Okay, what I'm going to do now is actually proving something very well known and simple. It's that a plus b times a minus b, that's a squared minus b squared. Okay, so everyone knows that. And I'm going to prove it, but it's not because that it's a super interesting proof, but it demonstrates a more general idea, and that is like what is algebraic thinking. Okay, on the surface we might just say that the first answer would be something like so it's working with letters instead of numbers. Okay, so if I ask that, okay, what is exactly the meaning of this? And you might say that, well, sure, yeah, this would be like, it means that 1 plus 2 times 1 minus 2. Well, let's calculate what that is. And that will be, well, okay, let's write it this way. It's 1 squared minus 2 squared. So this is 3 times, this is negative 1, and this is 1 minus 4, so this is negative 3, and this is negative 3 as well. Okay, so this is certainly a true statement. But I can do, you know, something else. A and B can be any real numbers, so I can write that pi plus the square root of 3 times pi minus the square root of 3. That's certainly the same as pi squared minus 3. Okay, because that's square root 3 squared. Okay, and so on. So this is another true statement. So we might say that, well, since we say that a and b can be any real number, so with this very tricky notation, now this is actually not a single statement, but it's like infinitely many statements, because I can have infinitely many choices for a and b, and I can produce that many statements. So here I picked a equals 1, b equals 2, here I picked a equals pi, and b equals the square root of 3. Okay, but I can pick any pairs, and this will be a true statement. So this is just a very nice and short way of writing down infinitely many true statements. Okay, so it's like the notation already has quite some power here. But it's more than that, because for a moment, let's just ask the following question. It's like, but how can we know that all of them are true statements? Okay, so it's like, well, we tried 1 and 2, and you can try this one, and you can try others. And if you calculate it, you will find that, yes, indeed, they are the same. Okay, so that's true. But how can you be sure that no one can choose an A and a B such that they would yield a false statement? Okay, so this will demonstrate that this is not just a good notation, very economical one, that we use the letters instead of the concrete numbers. We just say that, well, they are some real numbers, and we can write down infinitely many statements in one go, but we can actually prove it, because, well, pretend that we don't know. Okay, so what is a plus b and a times a minus b? Well, you can just do the cross multiplication. Okay, so that will be a squared minus a times b plus b times a minus b squared. Okay, so that equals. So now I can use effect. Well, it's like it's a law. I know that a times b equals b times a, because multiplication is commutative for real numbers. So I can just rewrite this as a squared minus ab plus ab minus b squared. Okay, and now if I look at this one, I don't know what a is and I don't know what b is. I don't care, but I know if I multiply them together, well, okay, I still don't know what that is. What is a times b? But if I add it once and subtract it once, well, yeah, that's just nothing. That's just 0. Therefore, I have a squared minus b squared here. Oh, well, that's exactly. Okay. So with just little reasoning, we proved infinitely many statements of this form to be true. Okay, well, that's a pretty powerful reasoning. So now we know that it's like, as long as you choose real numbers and you multiply them together, there is just no other way. This is going to be the way to go, and it will be true. So what's the point in this one? Well, beyond that's like, okay, this is the power of algebraic thinking, but what's the idea behind this? And the idea is abstraction. Okay. And as I discovered not long ago, if I just rely on you checking this in the dictionary, you may not get the meaning I'm using here. It's a bit surprising. But the meaning I'm using here is forgetting the unnecessary details. Okay, that's what we did. It's like, well, that's the idea of using letters instead of numbers. I don't care how big you are, it's just I care that, well, a is a real number. I don't care which, so it can be any. But I really don't pick any, because anything concrete. So I forget the unnecessary detail here. But this is, this is something we can do, because if you say the word apple, well, yeah, you already have the concept of apple. I don't have to describe one particular one, and it fits into this concept that you have green and you have yellow and you have red apples. But still, if I say apple, that works fine. So this is sort of the abstraction here, and that's the power of algebraic thinking, algebraic reasoning, forgetting unnecessary details.